right, I guess we can get started. So welcome everyone to another Computability Theory and Application Seminar. Today we're very happy to have with us Tim McNicholl from Iowa State University, and he will talk to us about which Lebesgue spaces are computably presentable. Tim.
Okay, well, thank you to the organizers for inviting me. And let's get started. So this talk consists of some things I've talked about before, some of my other talks on this stuff, so it's going to look familiar to people. But I also wanted to go deeper into proofs of some of the results. Some of these were things I previously thought were true, but didn't have the proofs worked out, but now the proofs are all worked out. But the central question I've been chasing remains. It's the question on this slide right here, trying to classify the Lebesgue spaces that are computably presentable. And so I'll get a little bit into this. I'll explain why there's an obvious answer to this question, and then we get a little bit further into this, and I'll try to explain why the obvious answer is probably wrong, or at least it's going to be very difficult to prove. So, let's see. Okay, here we go. All right, so, okay, so let's start off with just a little bit of big picture here. So, computable structure theory, something that goes, a long way back, and it's a, significant branch of computability and logic, generate a lot of challenging questions. But it primarily has focused on countable structures from algebra and combinatorics, and sometimes even regards uncountable structures as beyond its reach. Okay, but 2013, thankfully, that began to change. Okay, so Sasha McNicholl in 2013 suggested how we can start getting beyond the countable and getting up to the uncountable, at least at the level of separable structures. And it's kind of a simple idea. So we just take some of the framework of computable analysis, merge it with the framework of computable structure theory, and now we can start to do computable structure theory on things like Banach spaces, metric spaces, Banach lattices, and metric structures in general. So metric spaces have been investigated pretty thoroughly. Greenberg, Knight, Nies, Eng, Turetsky. Banach spaces, McNicholl and Eng had some results, and then myself with my student Tyler Brown and graduate students Joe Clannon and Don Stull have proven some things. So we're kind of now we're off the ground now. Okay, we're now comfortable going from beyond the countable up into the separable, uncountable level of the mathematical universe. So to explain a little bit about how we do this, let's first just take a step back and let's go over one way to set up computability on countable structures. Okay, so we're going to assume all of our structures have finite signature in this. So one way to get started, suppose we have some structure alpha. So alpha could be, say, a group, a graph, field, okay, and so A denotes its domain. Then a numbering of alpha is a surjection of the natural numbers onto A. Okay, surjection is that's the only requirement. It doesn't have to be bijective. So there could be lots and lots of repetitions. And then a numbering of, or if nu is a numbering of A, then we'll call this pair alpha nu a presentation of A. Okay, so in presentation, you think structure together with a numbering of the elements. Some presentations are computable, some are not. What do we mean when we say a presentation is computable? Well, we mean that, say, if you like, the pullback of the equality relation has to be computable. That is, we have to be able to tell if M and N number the same element of the structure, The pullback of each relation of the structure has to be computable, and the pullback of each function of the structure has to be computable. Okay, so we'll say a countable structure is computably presentable if it has a computable presentation. Okay, and so I've noticed here this is, it's a little interesting. Note this is a property that's preserved by isomorphism, even incomputable isomorphism. So it's really a property of the structure itself. It's not a computability theoretic property necessarily. Okay, so maybe some more intuitions. I like to think about this when we form a computable presentation of a structure, like a group or a field, or whatever. We're kind of imposing a notion of computability on the structure. Okay, we're saying how we're going to define computability on it, and we can think of computably presentable structures, therefore, as those on which we can compute. And computable structure theory then can be used as a study of computable presentations of mathematical structures. Okay, so all that is the more or less classical setup for countable structures. Now, how do we get up to the separable? Okay, well, it's really not that difficult. Okay, what do you have to do? You have to first define what do you mean by a presentation, some sort of separable, uncountable structure. So let's start with metric spaces. Suppose you have a metric space M underlying set X and metric D. Then a presentation of M is a pair consisting of the metric space and a sequence of points in M, more specifically a dense sequence of points in M. Okay, so of course we can't, just to back up a little bit here, we can't number the elements of M more than likely, because M could be an uncountable space like the reals or the complex numbers. Okay, so we kind of settle for second best. We don't try to number everything in the structure, we just try to number a dense set of points in the structure. And when we've done that, we call the nth point in that dense sequence the nth distinguished point of the presentation. Okay. Now, just as with countable structures, some presentations are computable, some are not. What makes a presentation computable? Okay, well, we might say it's computable if the distance function is computable. That's sort of pretty much true. That's not how we define it. So we have a presentation. We say it's computable. I'll kind of say roughly speaking first. It's computable if the distance function is computable on the distinguished points. Okay, now what does that mean? Because after all, if I take the distance between two distinguished points, I may not get a rational number. I may get an irrational number. May even get a transcendental number. Okay, so what does that mean to take in two distinguished points and output the distance? Well, we think about it in terms of approximations. Okay, namely, there's an algorithm that given any three numbers M and K as input, will compute a rational number Q. So that Q is within 2 to the minus K of the distance from PM to Pn. Okay, or another way to phrase this, we can compute the distance from PM to Pn with arbitrarily good precision. Okay, so many of the metric spaces we work with are computably presentable, and they have obvious computable presentations like the real numbers. We can just take our distinguished points to be the rational numbers, or in the case of the complex numbers, we just take the rational points in the plane as our dense set. Okay, so metric spaces are fun, but there's a lot of other kinds of structures in analysis, of course. So, one most common are Banach spaces. So, let's think a little bit about how do we set all this up on Banach spaces. Okay. First, let's start by recalling what a Banach space is. So, a Banach space is a normed vector space that is complete in the metric induced by the norm. Okay, so now when we say it's a normed vector space, that means it's got a field of scalars, right? So What are those? Well, they can either be the real numbers or they can be the complex numbers. So for technical reasons that are going to come up much later in the talk, we're going to restrict to real Banach spaces this evening. But everything I'm going to do in this talk holds for complex Banach spaces as well. The proofs and the definitions require some adjustment. Okay, but keep things simple right now. We're just going to think about Banach spaces over the reals. So some of our favorite Banach spaces, well, of course, Rn with the Euclidean norm is a Banach space. It's usually the first one we learn about. C01, the continuous real-valued functions on the closed unit interval. Okay, that's clearly a vector space under the usual pointwise addition and scalar multiplication. And then we take the norm to be the supremum norm, and that's an easy exercise to show that gives you indeed a Banach space. Okay, so those are two fairly simple examples. Okay. The kinds of Banach spaces we're going to be concerned with mostly in this talk are the Lebesgue spaces. So now, previous slides, I think, kind of review some stuff from undergrad analysis mostly. Now we're going to move up maybe to our beginning graduate analysis courses. So an example or an idea I like to keep in mind when I think about Lebesgue spaces is just a little observation from Calculus 1. Integral 0 to 1, 1 over x to the p dx is finite if and only if p is smaller than 1. Okay, so LP spaces are just kind of a very generalized form of this problem. You've got some function and you want to look at its p, or which values of p is its p power integrable. So let's actually get down to the definition. So suppose omega is our some measure space, and suppose p is greater than or equal to 1 but finite. Then we define LP omega to be the set of all measurable functions from x into r, so that the integral of the p power of the absolute value of f is finite. And the integral there is, of course, taken with respect to the measure mu. Okay, so again, this is a vector space, and is it a norm space? Yes, short answer. We can define a norm like this. We define the norm of a function f and LP omega to be the pth root of the integral of the pth power of the absolute value of f. Okay, now when we say that makes us into a Banach space, we're fibbing a little bit because the norm of a non-zero function can easily turn out to be 0. So how do we fix that? Well, we identify functions that agree almost everywhere. Okay, so when we think about LP spaces, we should think about the functions in the LP space as vectors, and those vectors are actually really equivalence classes of functions. Okay, so a little more terminology. When we say something's an LP space, we mean there's some measure space out there so that it's of the form LP of omega. And we say a Banach space is a Lebesgue space if it's an LP space for some value of p. So what we're going to be looking at is, if you will, how do we compute on LP spaces, and how which LP spaces, which Lebesgue spaces are computably presentable in the sense I'm about to describe. Okay, so all that was very abstract, but it's going to turn out that if we're just looking at separable LP spaces, which we will, there's actually not too many of them. Okay, so here's some prime examples of LP spaces. Okay, so first is LP01. Okay, well, we just look at the Lebesgue measurable functions on the unit interval. M is the usual Lebesgue measure on 0, 1. Then we can start to do games like the following. We start with the natural numbers and then take the counting measure on the natural numbers, and then we can take that space's LP space, and we call that little LP. And short little calculation to see that what we're really talking about here is the p-summable sequences. In particular, the p-norm of a sequence Sn is just some 0 to infinity absolute value Sn to the p, all raised to the 1 over p. Okay, so there's another kind of LP space. Then if we just take the finite set 1 through n, and then we take the measure mu to be the counting measure on that set, and then we form the LP space of that measure space, what do we get? Well, again, we do a little calculation. We get the set of p-summable, it's p-summable sequence. We get the usual little LPn, that is the little LP norm on the space Rn. Okay, that is to say, the p-norm of a finite sequence S1 through Sn is the sum absolute value S1 to the p plus absolute value S2 to the p up to absolute value Sn to the p, all raised to the 1 over p. Okay, so LP spaces, as defined, they're kind of very abstract, but they have lots of concrete examples. And it turns out these three are pretty much all of the LP spaces in the separable case. Okay, so as we'll see later in the talk. Okay, so I talked, kind of getting back to the computability theory now. I talked earlier about, okay, well, how do we lift computable structure theory up to separable but uncountable structures? And I walked through how we set this up with metric spaces. How do we do it with Banach spaces? One way is you can say, well, presentation of a Banach space is a presentation of the underlying metric space that makes the operations of vector addition, scalar multiplication computable. That's a perfectly fine definition. I'm not going to argue against it. I just don't want to get into talking about what it means for a function on a Banach space to be computable with respect to a presentation. So I'm going to take a shortcut around that, which is essentially due to Perel and Richards. And it goes like this. So B be a Banach space. So a presentation of B is a pair like this, B together with a sequence Bn that isn't necessarily dense, but is at least linearly dense. Okay, what do we mean by that? We mean that its linear span is a dense sequence in the Banach space B. Okay, or here I rephrase that another way. B is the closed linear span of the terms of the sequence. Okay, and then as we set things up with metric spaces, if B sharp is a presentation of a Banach space B, then we'll refer to Vn as the nth distinguished vector of the presentation. Okay, so that means now to define a presentation of a Banach space, all you have to do is specify what your distinguished vectors are. Okay, a little more terminology than we look at some examples. So suppose we have a presentation B sharp of a Banach space B. A rational vector of B sharp is a rational linear combination of distinguished vectors of B sharp. It is a vector expressible in the form sum j equals 0 to n alpha j bj, where each alpha j is a rational scalar and each bj is a distinguished vector of B sharp. And then once we define rational vectors, we can now say, what do we mean by a computable presentation of a Banach space? And so I'll start by saying it kind of roughly first. So roughly speaking, a presentation of a Banach space is computable if the norm function is computable on the rational vectors. Okay, spelling that out a little bit more. Again, when we take the norm of a rational vector, we're not going to get a rational number, we're going to get a real number. That real number may have a non-terminating decimal expansion. So what we have to, again, think about this in terms of approximations. So when we say it's, B sharp is computable, we mean there's an algorithm that given a number k and a code of a rational vector v of B sharp computes a rational number q that's within 2 to the minus k of the norm of v. Okay, and So it's just keeping things in context. It's defined a lot like, in some ways, a lot like we define computable presentation of a metric space. Okay, instead of saying distances between points or distances between distinguished points or can be computed, we mean norms of rational vectors can be computed. Okay, then some terminology that's going to come in the block. A code of such an algorithm is what we call an index of the presentation. Okay, a little more terminology. Like all these presentations of Banach space, one may be kind of designated as standard by practice. And in that case, we identify the space with its standard presentation. So an example of that, standard presentation of R, we can just take 1 to be the nth distinguished vector for all n. And when working with C01, the natural thing to do is to present it by declaring the nth distinguished vector to be the nth power of x. And then by the Weierstrass approximation theorem, that's a linearly dense subset of C01. And little calculus exercise in the second case, but it's easy to see these are all computable presentations. How about the Lebesgue spaces? How do we present those? Well, the standard presentations of little LP and little LP are defined by just the standard bases for those spaces. And it's easy to see that those are computable. The standard presentation of LP01, we just take indicator functions of the dyadic subintervals of 0, 1, and then it turns out that's linearly dense in LP01. Okay, you might not think there's much of a difference between these spaces, and really, in some ways, there's not, but later we'll also want to talk about LP open interval 0, 1. There's just no difference here. Just chop out 0 and 1 from your dyadic subintervals. And then later we're going to have to deal with this space LP, and then we're going to take the standard Lebesgue measure on open interval 0, 1 and take countable, take its countable Cartesian product, and that's just kind of defined in the natural way. Take nkth distinguished vector to be indicator function of 0, 1 open interval to the n times kth dyadic subinterval times open interval 0, 1 to the omega. And again, it's that's hard to see. All these presentations are computable if that number p is computable. Okay, so to get back to our question, we want to know which Lebesgue spaces are computably presentable. Okay, so this is a natural class to study from computable structure theory's perspective. So the first thing you want to know is which of these spaces can you present? And well, let's just start this kind of silly observation right here. Every computably presentable Lebesgue space is separable, right? Because they all have linearly dense sequences. Okay, so you can just take their sets of rational vectors are dense. And that's a really good thing because there's not too many separable LP spaces. So we think about two cases. First, a case where the exponent is 2. So classic theorem, if B is a separable L2 space, it's either little L2 or it's little L2n up to isometric isomorphism. Okay, so there's not too many of those. And of course, those are also the separable Hilbert spaces. Okay. What about exponents other than P? Well, again, there's not too many of them, but we need a little tool now to describe them called the LP sum of two Banach spaces. And that's this structure I'm defining here. So what you do is you take your two Banach spaces, B0, B1. You start with the external direct product and make that your vector space. And then to get a norm on it, you define norm of B0 comma B1 to be, well, P's power of B0's norm plus P's power of B1's norm all raised to 1 over P. Okay. So it looks kind of like you're taking the procedure for making little LP2, but you're replacing absolute value with the norms of these Banach spaces. You're replacing the numbers with vectors from these Banach spaces. Okay. Now, with that set up, we get this classical theorem I've seen attributed to Grafendorf. But it goes like this. Suppose P at least one with finite and not two, then the central LP spaces are the following. They can be just LPn for some positive integer n, little LP, LP0, 1, or a LP sum of 2 of 1 through 3. Now, in particular, I can take little LP plus LP0, 1, or little LPn plus LP0, 1. Okay, and so every central LP space is isometrically isomorphic to exactly one of P5 spaces. So, yeah, we started out when we defined LP spaces, we had this big abstract definition. Once we get down to separable stuff, all that abstractness, I think, kind of goes away. There's just not too many of them. Okay. And a little corollary of all that is, of course, if P is a computable number, okay, that's at least one, of course, then all your separable LP spaces are automatically computably presentable. Okay. So we would like to know, does the converse hold? Okay. That is, if there's a computably presentable LP space, does it follow that P is computable? Okay. And a few moments of reflection revealed the answer is no. Little LP1 is the same thing as little L1, so it doesn't matter what P is. Little LP1 is a computably presentable space. Okay, so in future, we rule out that sort of thing, and we insist everything have dimension at least 2. Okay, so let's rephrase our question now. If there's a computably presentable LP space whose dimension is at least 2, does it follow P is computable? Okay, I think the answer is obviously yes, but I'm not sure that's right. In fact, I tend to think it's actually wrong. But let's just think through what are some impacts of this answer. Why might we want to get into this question? If the answer is yes, then we're going to know a lot. We're going to know which Lebesgue spaces are computably categorical and their degrees and categories to those that are not. Based on papers by myself, Tyler Brown, Joe Clannon, and Don Stull. And we would likely be able to pin down complexity of the index set of all Lebesgue space presentations. So Tyler Brown, Sasha Melnikoff, and myself have shown that that index set is, whoops, I got those numbers mixed up there. I apologize for that. No, it's pi03, not pi30. But we were never able to get any lower bounds for that. And the reason why we just kept bumping into this issue of, okay, well, if we've got a presentation, what information does that give us about the exponent P? Okay. If the answer is no, then that means we're going to be a long way off from knowing everything there is to know about computability and Lebesgue spaces. Okay, maybe that's a good thing. If you're looking for lots of problems to work on, in my case, I would really like to get to a point where we know everything about this stuff. So the answer of no in some ways would be disappointing. But I do, at this point, I think actually the answer is no. Okay. Okay, so let me share some partial results on this. So let's first go to the finite dimensional case. So in that case, the obvious answer is right. If n's at least 2, and if little LPn is computably presentable, then P's got to be computable. And the proof is kind of a brute force search procedure. And the reason why that search procedure works is because the unit ball in any finite dimensional Banach space is compact. Okay, so let's move up to infinite dimensional cases where we no longer have a compact unit ball. What can we do? Well, if P is at least 2, then again, the obvious answer is right. Okay, that is, if there's a computable presentation of a space whose dimension is at least 2, then P has to be computable. This time, again, we can't use the compactness of the unit ball. So we use what's essentially a pi01 classification of Banach spaces that embed into an LP space due to Crevine. And he didn't call it a pi01 classification, but that's really what it is. He gives an infinite list of norm inequalities so that the Banach spaces that satisfy all of those norm inequalities are precisely the Banach spaces that embed into an LP space. Okay, now what happens if p is smaller than 2? Well, here's where the problems start. So for p less than 2, the best result to date is this one by, again, Tyler Brown, Sasha Melnikoff, and myself, that p is less than 2, and if there's a computable presentation of an LP space, again, with dimension at least 2, then p is at least right CE. But that's the best we've got so far. And the techniques there is we traded off on a formula for the modulus of convexity for an LP space due to Olaf Hanner. And so that's what kind of how we were able to cook up this proof. Okay, so those are all kind of partial results or partial positive results. Okay, now I want to share a partial negative result. So you might make us think that maybe this is, obvious answer is no, or maybe this is something that's not computable. So I'm going to at least show that maybe it may be computable, but it's not uniformly computable. Okay, specifically, there's no computable function that can take an index of a presentation of a Lebesgue space and spit out the exponent of that Lebesgue space. Okay, in particular, it kind of gets even worse. You even just start with an interval I, and you even just allow yourself to start with the assumption that you're only dealing with Lebesgue spaces whose exponent lies in I, and the situation doesn't get any better. You still can't uniformly compute exponents of Lebesgue spaces from Banach, from their presentations, even when you know the exponent lies inside that open interval. So you would think that if it's not uniform, well, then maybe if you know about a few norm inequalities, that might give you enough information to be able to compute the exponent, but this is kind of saying no, even that won't do it for you. So I want to spend a little time talking about the proof of this theorem because I think it's a fun proof. I also think it's interesting because it's going to lead us into some computable probability theory. So first, little result about uniformly presenting Banach spaces. So when we have a sequence of Banach space presentations, it's uniformly computable if you've got a function that computes an index of the presentation of BE from E, and then a sequence of Banach spaces is uniformly computably presentable if there's a uniformly computable sequence BE sharp E and N of presentations of those spaces. So one lemma we're going to use in this non-uniformity result is this lemma here, and just for future reference in this talk, I'm going to call it the uniform presentability lemma. So suppose B0 and B1 are computable presentations of Banach spaces. Suppose we have a CE set A, and for each natural number E, let's let A, E be B1, say if E is not in A, B0 if E is in A. Then if I've got a computable isometric embedding of B1 sharp into B0 sharp, then this sequence is uniformly computably presentable. So this kind of gives me a way to code behavior of CE sets into sequences of presentations of Banach spaces. The next ingredient is we're going to need an effective embedding result. Specifically, we're going to use this. If I've got this situation, PR computable real, so that P is at least 1, less than R, less than or equal to 2, and there's computable isometric embedding of little LR into LP01. Now, where's this coming from? Well, it's an effective version of a famous result due to McNicholl, Cassel, and Cravine, which just says little LR isometrically embeds into LP01 when P is less than R, less than 2. Proof of that theorem was one of the first applications of, I think it's got two things. It's one of the first applications of probability theory to Banach space. It's also one of, and then an extension of this theorem was the first application of ultra products to Banach spaces. But in particular, the proof uses the theory of stable random variables. which, before I got into this project, I had not heard of these, but of course, I'm a computability theorist, why would I? But then I talked to some folks I know work in probability theory, and they had not heard of them either. So anyway, this was kind of fun. Get to learn some more mathematics. So for this effective version, we're going to need an effective theory of stable random variables. Okay, so crash course in stable random variables. So let's say we've got a random variable x. It's called stable if whenever you have two positive numbers a and b, there's going to be a corresponding positive number c and a real d, so that whenever x1 or x2 are independent copies of x, that is, they are independent and have the same distribution as x, ax1 plus bx2 is, or has the same distribution as cx plus d. Okay. In addition, if we can always choose that number d to be 0, then x is then called a strictly stable random variable. Okay, so usually when I talk about this, the first thing that happens, people say Gaussian. Yeah, that's right. Every Gaussian distribution is stable. Cauchy distributions are another example of stable distributions. If you're wondering where did these come from, they actually, I understand the first paper to talk about a stable distribution was a paper, I think it was in 1932 in astrophysics, and the concept just kind of developed from there. Now, these stable random variables, again, maybe that's a bit of an abstract definition, but there's a really nice way, a fairly nice way to parameterize these. Okay, it turns out every stable random variable is described completely by 4 numbers. Okay, the first of these numbers is called its index of stability, and it's in a sense essentially defined by this theorem. If x is stable, there's a unique real number, so that number c in the previous definition is the rth root of the rth power of a plus the rth power of b. Okay, and that number r is called the index of stability of the random variable x, and then we say that random variable x is an r-stable random variable. Okay, what are these other numbers that describe a stable random variable? Okay, well, let's call, when we're doing probability theory, when we talk about characteristic function, we don't mean what we mean in computability theory. We mean the expectation of e to the I xt. And the reason why we do such a thing, two random variables are identically distributed if and only if they have the same characteristic function. So it gives us a test for having the same distribution. When x is a random variable, if it's r stable, then there are numbers sigma, beta, and delta, so that the characteristic function has this great big awful form right here. Fortunately, this big awful form, really, we won't see it again. We just have to know it's out there. Because it tells us about these numbers, and these numbers have names. So sigma is called the scale parameter, delta is called the shift parameter, beta is called the skewness parameter. Okay, so every stable random variable has these 4 parameters, and let's back up a little bit. Those 4 parameters completely determine the stable random variable up to distribution. Okay, so let's build up an effective theory of these things. So the first thing we'd want to know is, okay, if the parameter is computable, can you make a computable random variable with that distribution? And the answer is yes. And that's not too hard to show. You just sort of take an inversion formula out of Jared and just kind of work the computations. Okay. And then an effectivization of a classical result, if x are stable and if its parameters are all computable, then if we want to take the expectation of the pth power of the absolute value of x, or the pth moment of x, that's computable provided p is less than r. Okay, what happens if p is at least r? Well, then actually that expectation is infinite in that case. However, if r is 2, then this moment is computable for all non-negative reals p. So again, these this theorem, like the previous one, just more or less straightforward effectivizations of classical results. Okay, then getting a little deeper into the computability theory. Suppose P are computable reals, so that P is less than or less than equal to 2. Then if we have a stable distribution, whose parameters are computable and whose stability indexes are, then LP01 contains a computable vector whose distribution is mu. Okay, so that's just kind of putting together the pieces from those previous two theorems. Okay. Now, getting back into Banach spaces, so we have a Banach space B and vectors V1 through Vn and B. And define what I mean when I say they are LP formally disjointly supported. Okay, so disjointly supported in the context of an LP space means you have vectors whose supports are disjoint from each other. Okay. Such vectors would satisfy this identity that I have right here. So you're in an arbitrary Banach space, you've got vectors V1 through Vn that satisfy this identity for all choices of scalars. You'll call it an LP formally disjointly supported sequence, meaning it's behaving like a sequence of disjointly supported vectors in LP. How far can we push that analogy? Well, turns out that if you're in an LP space, of course, then disjointly supported vectors are in fact LP formally disjointly supported by a wonderful result of John Lamperti going back to 1956. I think if P is not 2, then you get the converse. LP formally disjointly supported vectors and LP omega are also disjointly supported. And the reason why we care about these things, it turns out this wonderful fact right here, I shouldn't call this a wonderful fact. This is an effectivization of a wonderful fact. Suppose P is at least 1, less than R, less than 2, and we've got Gn, an independent family of symmetric and strictly R stable random variables in LP, omega R, then Gn is LR formally disjointly supported. So having things R stable and independent gives you LR formal disjointly supported vectors. And then kind of working the previous theorems, that's hard then show this, you can get a computable sequence Gn vectors in LP 0, 1 omega R, so that each Gn is symmetric, strictly R stable. Again, here R and P need to be computable. And it's an independent sequence, okay? So these are going to be LR formally disjointly supported, even though they live down in LP. And now maybe you can see what's coming next. We finally get our proof of this effective embedding result. And we take that sequence of vectors Gn I just talked about. They're all non-zero. You just normalize all of them, and then you define a map from little LR into LP01 like this. T1 of F is some F of n Hn. Okay, so that's clearly linear, and then just work the algebra. Since Gn is LR formally disjoint supported, it also gives you an isometry. Okay, then follows that's a computable map. It is mapping a standard basis onto a computable sequence. Okay, unfortunately, I didn't land in LP01 here like I wanted to. I landed in LP01 omega. No big deal. By theorem, Clan and McNicholl Stahl, there's a computable isometric isomorphism of LP01 omega onto LP01. So compose those maps and you're done. Okay, finally, now we can prove this non-uniformity result. So we're going to follow a familiar kind of pattern. We'll assume such a function exists, and then we'll hit it with the recursion theorem. So suppose such a function f like this exists. So again, what f does, it takes indices of Lebesgue space presentations and computes their exponents, provided the exponent lies in this interval I that we're given. And then we're going to fix rational numbers R1 and R2 and number k0, so R2 minus 2 to the minus k0 is larger than R1. Okay, so R1 is less than R2, so 2 to the minus k0 is kind of gives us the ability to move a little bit left of R2 without hitting R1. Now we're going to take all the numbers E in the domain of F so that K0 belongs to the domain phi F of E, and nu Q phi F of E of K0 is within 2 to the minus K0 of R2. And if you're wondering what's that nu to Q, well, that's just a coding, some standard coding of the rational numbers. Okay, so that's a CE set. Okay. Now we're going to make a sequence of Banach spaces. So BE, BL, R101 if he is an S, little LR2 if he is not an S. Okay, by that uniform presentability lemma from several slides ago, that's uniformly computably presentable. So we've got a function G. So G of E indexes a presentation of BE for all E in the natural numbers. Okay, now I bring in the recursion theorem. We get an E0, so that's B. GE0 is BE0, so E0 indexes B. E0. Now I work the cases. If E0 is not in S, okay, then if we work the definition of S from previous slide, if the E0 has to be little l R2, but again, by the conditions on S, F of E0 can't index R2, so F failed in that case. So what's up? Well, maybe E0 is an S. Well, then in that case, BE0 has to drop down to capital R101. Again, because E0 is an S, F of E0 can't index R1, giving an answer that's too far off. So either way, we get a contradiction, and then that rules out the existence of a function little f as desired. Okay, so to sum up here, so we began with the question, which Lebesgue spaces are computably presentable? That is, which Lebesgue spaces can we actually compute on? So of course, we observed that when P is computable, all of our separable LP spaces are automatically computably presentable. And then that leads to the question, well, does the converse hold? We saw immediately the answer is no. But we showed the answer is yes, at least when P is at least 2 and dimension is finite, and I'm sorry, and when the dimension is finite. So that left us down to the case P less than 2. And what have we got there? Well, the best we can do there right now is show the P is right CE if there's a computably presentable LP space. And okay, and then since we're having trouble computing this, maybe we ask, well, at least is there? Can we show there's no uniform way to do this? And answer is yes. There's no uniform way to compute exponents of Lebesgue spaces from their presentations, even when you're kind of advised that the exponent has to lie inside some maybe tiny open interval. So to me, this it's not a proof, but strong evidence that this result in item 5 is the best possible. So my conjecture now is that if P is at least 1 less than 2 and right CE, then LP01 is a computably presentable space. But don't ask me how to do that. I don't know. I just think that if there were a proof of that, then it would have to be at least uniform, at least on small intervals, and that's just not possible. Of course, on the way we developed an effective theory of stable random variables, which I think are just kind of interesting and beautiful in their own right. So I'll close out with some references. So the Computable analysis papers I refer to are these. To the results about the complexity of Lebesgue space index set being pi 0.3. That's in this paper by Tyler Brown, myself, and Sasha Melnikov that just got accepted to JSL last week. Preprint is on the archive. then the degrees of categoricity of the LP spaces of P computable were nailed down in these two papers by McNicholl, Clannon, Stahl, and Brown. Little LP's degree of categoricity was nailed down in this paper by myself. Most of the stuff I talked about in this talk, at least as far as the stable random variables, that computable embedding results, and the non-uniformity results are in this paper. Computing the exponent of the Lebesgue space, which is under review. Preprint is on Archive. The classical analysis references. So the result quoted by Crevine about the pi01 classification is in this paper, and then the wonderful results about embedding little lr into LP01 using stable random variables is in this paper. And then if you want to learn more about stable random variables, I really like the book Stable Non-Gaussian Random Processes by Lebesgue and Taku. It's almost encyclopedic. Anything you want to know about these kinds of random variables, including the complex versions, it's all in there, and all the proofs are pretty much worked out in there. So that's if I want to know something about these, this is a good first place to start. Okay, and with that, I'll conclude my remarks, and thank everyone for their attention.
Thanks so much, Tim. That was great. So let me open it up to questions. If does anybody have any questions for Tim, or any comments, anything?
Invective. No.
I have a question. Are you able to hear me?
Yes. Hi, Linda.
Hi. I was wondering so for the non-uniformity result, if you declare in advance that all of the spaces are going to be little LP spaces for some P, or that all of them are going to be big LP spaces for some P, then do you still think that you can get a similar non-uniformity result?
No. I mean, I'm not sure. That would be a better way. So the thing that drives that proof again is that ability to embed the little lr into the cap LP. Okay, so you can also do that with big LR. So LR01 computably isometrically embeds into cap LP01 when P less than R less than 2. Okay, and so they just comment a little bit about that result. Again, that's an effectivization of one of the results in this first paper on in the classical references. And that result was originally proved, I think this is beautiful, using an ultra product technique. Then I kind of reproved it using the compactness theorem from continuous logic, and if you believe that that's an effective principle, then there's an effective embedding. So I would say that if you're just going to restrict down to cap LP spaces, you're going to get the same thing. The little LP spaces, I've never been able to nail that down. I don't think there's an embedding result like this. Somewhere, I thought I saw somewhere one time that in fact there are no embeddings between those spaces. That every time I try to track down a source, I can't find it, and I can't prove it myself. So I don't think you could. I think if you just restrict yourself to the little L spaces, and maybe this would be a good place to start next. You actually could compute the exponent. But that's a great question. Thank you.
Thank you.
Are there other questions for Tim? scrolling through this to see that I don't miss anyone. Okay, well, so if not, let's thank Tim again, either audibly or however you like to do it. Thanks a lot, Tim. And so now we have our tradition in this seminar of sticking around a little bit for anybody that's interested and catching up, chatting a bit.